Okay, so this will be our first example in solving an exact differential equation. We're going to look at the equation 2xy dy plus the quantity y squared minus 2x dx equals 0. And we want to figure out what's the solution for this differential equation. And so what we're going to do is we're going to look at our quantity here. And so this is in front of the dy, so that was our n. So we're going to take 2xy and differentiate with respect to x. That'll give us 2y. And then likewise, we're going to take our m, the thing in front of the dx, and differentiate that with respect to y. So we got 2y squared minus 2x with respect to y. That's going to be 2y. And so it turns out that this is exact, and that means that we can proceed as we plan. So remember, our goal is we want to figure out what's the function f of xy, so that f of xy equals c is our solution. Okay, and so what we know is that this quantity, y squared minus 2x, so we know that y squared minus 2x is equal to the derivative of our function f with respect to x. And so what that means is that remember that these are partial derivatives, so we can just anti-differentiate both sides with respect to x because we're undoing a partial derivative, and that tells us that f of xy must look like this. It must be xy squared minus x squared plus some function of y, because if I had a function that was just involving y, so whenever we took the partial derivative with respect to x, it would disappear like a constant. So that's what the function f of xy looks like. Now, how do we figure out what this g of y is? There's two ways, but well, they're all equivalent ways, but I think the easiest way to get at it is to realize that if this quantity was the partial with respect to x, then the other quantity was the partial with respect to y. So you could do the same thing with the other one, undo this 2xy, undo that partial with respect to y, and compare, and that's fine. But what I think is easiest is actually just to use what we have already, differentiate that with respect to y, and then set that equal to what we know it should be. So we know that f sub y, on the one hand, if we just differentiate this with respect to y, this is going to give us 2xy. The x squared will go away because we're differentiating with respect to y, plus just the ordinary derivative of g, because we're just differentiating that with respect to y. So that's our f sub y. And we know that this should be equal to, so we have two different expressions now for the partial of f with respect to y. We have 2xy plus gy prime, and we also have just 2xy. And we know that those have to be equal. So since 2xy plus g prime of y equals 2xy, just setting those two different expressions for the same quantity, since they're the same quantity, they're equal to each other, so setting them equal, that tells us that g prime of y is 0, and therefore g of y is some constant. Okay, and so it turns out what's going to happen is our solution is going to be, so our solution is going to be xy squared minus x squared plus some constant, we can call it c1, equals another constant, c2. And then, of course, we can do the usual thing where we can just roll up c1 and put it in c2, so subtract c1 from both sides if we want to be fancy about it. I'm just going to do this the iPad magic way, and then move the constants over on one side, call it c. Okay, so it turns out that this is going to be our solution. Now, this is no longer a function y equals f of x, because we're not able to explicitly solve this for y, but we can still do all the stuff that we did before. It's kind of like doing implicit differentiation in Calc 1, but this is our solution. So this family of curves xy squared minus x squared equals c will satisfy, those are exactly the things that will satisfy our differential equation.